I'm gonna write it like this. PQ, you know how to get a vector from points.
Yeah.
1, 4.
4.
What's vector PR?
2 and 8.
2 and 8?
Yeah.
What's that? Let me make that a big dot. What's that dot product? Sometimes it helps if you put it underneath it. That times that plus that times that.
32.
34?
34.
Alright, inverse cosine. 30. This would give me the angle between these vectors PQ and PR. Here's my angle. Inverse cosine. Now, what's that magnitude? Root 4 squared plus 1, 17. Very good. Now, what's square root of 2 squared plus 8 squared?
64 to 68.
68? There you go. You have to type it if you don't want to. There you go. Two space. Works in two-dimensional space. Absolutely. Dot product. Next class, we're going to do something called a cross product. Anybody heard of that? Okay. They're awesome. Those have to be three-dimensional vectors. So if you want to do something in two space, just make the z component what? 0. Cool. Hey, you ready for the last problem? You sure? Alright, and when there's something else, like I said, this thing keeps going and going, right? Who has to do, like, maybe it's a physics class? Have you ever found something called work? Work is equal to force times what? Thank you. Work equals force times distance. Don't worry if you're sitting in the class like, man, everyone in this class is so smart. But they know this stuff. They've seen this before. Work is equal to force times distance. Absolutely, if it's a constant force. But now, we can use this with displacement. And we can say this. We have a force vector and a displacement or distance vector. Then we can say this is work. So right here, when I'm going to write work, and I'm going to pick a problem in the textbook, we'll work it out. Work equals magnitude of force times dot magnitude of distance, which means it's going to be the magnitude of the force vector. Maybe it's like 12 pounds or something. Magnitude of the distance vector, or displacement. And then the cosine of the angle, where art, again, the angle is the angle between the what? The two vectors, right?
Mm-hmm.
And so you think about everyone, I mean, what has a design like this in this world where this is important? I'm thinking, you know, like, what's the work necessary to tow like a car? Like, here's the tow truck, and there's that chain going down here. So the textbook, let's look in here. They usually do like the mom pulling the kid with the sled, right? You got the rope, and you got the force there, and the distance she pulls them, or it's the tow truck pulling the car. Let me see. Let's end on this note. This is in 12.3. Well, okay, first of all, I went on page 829. I see the little, see it? See the wagon? All right, there's it. We're not doing the wagon problem. Come on, do they have a tow truck? Oh, 50 has the tow truck. 51 has the sled. Okay, let's do 50. A tow truck drags a stalled car along the road. The chain makes an angle of 30 degrees with the road. Let's start drawing a picture. And when the chain makes an angle 30 degrees with the road. Alright, there's the chain. And they give you the tension. And that's the magnitude of the force. They said the tension in the chain is 1,500 newtons. So this chain right here, when this tension, if you want to write magnitude of the force, that's that tension. It's given as 1,500 newtons. Pulling that car. How far is it going to go? How much work is done? How much work is done? By the truck in pulling a car 1 kilometer. By the truck. Pull the car 1 kilometer. Now let me start with that 1 kilometer. It's appropriate when we talk about work. Did you cover work in calculus 2?
Yes.
Yeah, it's like, in this Stewart text by one, it's chapter 6. But you probably recall this, things were either in foot pounds or in Newton meters. Did you do it in Freeman's class?
I don't remember, maybe, yeah.
Anybody in here in your was Freeman's class with you? Anybody else take Professor Freeman? Cool, he is Professor Freeman. Hey, so Professor, but work, it's, you put in what? Newton meters or, just for work, you put in Newton meters or foot pounds.
Football.
Well, that's kilometers. So let's start out. What's that in meters? 1,000. So I'm going to change this out in 1,000. You go, why? Because it's good to write our answer in Newton. Because what is Newton meters? Starts with a J. Joules. And we can just write our answer. The work is blah 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 joules. Cool. Joules being Newton meters. So we got 1,000. So we're going to go 1,000 meters. The angle's 30 degrees. So you can say, what's my displacement vector? That's the magnitude of it. So the magnitude of the displacement vector is going to be what? 1,000 meters. What's the magnitude of force?
1,500 meters.
1,500 newtons. Now these are just numbers I'm going to multiply. Cosine of what angle? 30. Oh, what is the cos of 30? That's ugly. Root 3 over what? 2. I want use that call it the calculator, but cosine of 30, I see it right there. Two special right triangles. I'm getting 1, 5. How many zeros in there? 1, 2, 3, 4, 5. And then I'll multiply a root 3 over 2. Now what's 1/2 of 1.5 million? 750,000 Newton meters? Oh, I could just put a big J for what? Joules. Now when joules is spelled this. Joules. And it represents Newton meters.
You need to square it.
You know?
Square root of 3 multiplied.
Oh, you're the best. So he's like, don't forget that square root of 3. Thank you so much. People be watching the video going, that's messed up. Thank you very much. Get that root on there. And there's the J for joules. Pull this down. Hey, cool job. Good job with this stuff. Can I do 2 more right before you leave? You sure? All right. This is it, Owen. This is the last thing. This is from dot product. It's a component. It's called a component of a vector B along A. I'll put it right here. I gotta leave that though. I need this, dude. All right. Here it is. Oh, this will only take a second. Let's say that's vector V, and this is vector A. In this section, the author talked about a component of B along A. So, and here's a theta, right? It's like the shadow. So I'm just going to drop from here a dotted line and stop here. And then when I'm talking about from here to here, that, from that length to there, this part to this part, I'm going to call that the component of vector B onto A. So I want to make sure when the component of B onto A goes from here to here. Let's come up with a math formula for that. Do this. So let's start out, everyone. I see cosine in here. What's the cosine of theta equal to? Cosine of theta equals SOHCAHTOA, component, right, of B along A. Yeah, the author writes COMP and puts a B here and an A as a subscript. Can everyone see that? That's the notation. You'll see it on my formula sheet and in the textbook. It's talking about this length right here. Oh, let me make sure that's 90 degrees. Here. All right, it's just from there to there. Cosine theta equals adjacent over hypotenuse. So what's this over?
B vector.
All right. So now, can I substitute that there?
Yep.
Yeah, let me do it. All right. Oh, and shouldn't I, if I want, I'm talking about this magnitude, right? So what should I put around this? Do you all agree? If I'm saying the cosine of that angle is this divided this, we're going to invent the formula for component B along A. Well, that would go here. That's that. That's that. Now when I want you to isolate this math formula for component B along A, what do you get? It's going to get pretty neat. What would be the math formula we're going to use on a formula sheet for that would always represent component of B along A?
So if,
Anything cancel over here.
yeah, the B cancels, right?
Everyone see this? You ready? And you just got to divide to what? So there it is. I'm going to write it down really big. Component B along A will always equal the dot product of A and B divided by the magnitude of that vector array. Now, everyone, do you agree that's a scalar value? So I want to make sure we understand that. You go, this is a scalar. That's not a vector, is it? It's like a magnitude. It gives a length. But I have to be careful. This can become negative. When I teach down Naval Academy, I met that off a couple of the midshipmen one time because most of the textbook problems came out positive. Dot products can come out negative. So I want to point that out. All right, now, that's called the component B along A. Now what about the vector right here? What would be the vector represented? It's along A, right? Well, we call it the vector projection of B onto A. So I'm going to put that down. PROJ B onto A. That's the notation. But I want you to help me invent this. All we need is that. Cool? Hey, do you all agree? Doesn't this basically represent the length of the vector?
Mm-hmm.
So remember that problem I did, and this is the reason I did that problem earlier. Remember that problem I said, find a vector that has a length of 6 and it was in the same direction, remember that? That's what I'm going to do right now. To figure out the formula for the vector projection, I'm like, let me take vector A, let me shrink it to a unit vector. What would that be? And do you agree that's a unit vector in the direction of A?
Mm-hmm.
But then, that would only have a length of what? 1. If I want this vector, I want to think about what it is, as long as it goes in the same direction of A with a length of 1, then I multiply the component to it, you now have the vector. Because that would give the actual what? The actual length multiplied in front. So in front of this, everyone, I'm going to put, what is that? A dot B all over the what? Magnitude of A. Now I put this in words on your formula sheet. This is called the component multiplied, what's this over here? A unit vector in which direction? A unit vector in the direction of which vector? So me, everyone, that's how I memorize the formula. It's a conceptual understanding. A vector projection of B onto A is really the component times the unit vector in its direction. I know the component is this. If I ever forgot it, I can figure it out by SOHCAHTOA, it wasn't this. Everything comes from this. And it's this times this. Now, did anybody want to clean that up? Because what's the magnitude of A times the magnitude of A? So if you want to write this another way, when this is how the author writes it, he goes, vector projection of B onto A is A dot B all over the magnitude of A squared, and then the last thing left over would be just this vector what? Vector A. Cool. So here's your two vectors. 1, 2, and 3, 7. This is vector A. This is vector B. Last problem. Everyone, can you find this? I just made up two vectors. It's in two-dimensional space. I could have chosen three-dimensional vectors. I thought I would just choose what? Two-dimensional vectors. Can you find the vector projection of B onto A? Here's vector A. Here's vector B. All right. First of all, what vector goes over here? It's the one that's the subscript. So what's vector A? 3/7. What goes here?
Isn't it 1, 2?
It's 1, 2.
Oh yeah, thank you. 1, 2. You're the best. Hey, what goes here now?
Your dot product,
Do the dot product. What's the dot?
17.
3 times 1 plus 2 times 7, 17 over. What's that magnitude? But then you got to square it. It's going to lift the radical off.
9.
5, right? You agree?
Oh, yeah, 5.
And
Yeah, 5.
then we take the radical off. Do you have to distribute it? Unless you want to. You see that? Everyone, again, I know our class ends at 2:50. I wanted to leave the last 10 minutes to talk to people. They got me to, I gotta sign this document. It's the first day. People might have to tell me about, like, I have an interview on this day or anything with that. Cool. If you have any questions, stick around. Super job.
Wouldn't you have to square the 5?
It's a square. Yeah.
Great question. That's a there's a common error in there, but remember, it was like, the magnitude of A was what?
5.
That, you agree?
Oh.
And we go, but then we square that, and it takes the radical off it and makes it just a what? 5. Hey, so it's interesting, this projection, it wasn't shorter than the long vector A, it was what? Wouldn't it be longer? Yeah, because sometimes the vector goes way over the little vector. It's like a shadow. Hey, great job, everyone. See you on Thursday.